Hey there, it's Shannon Math Chick Myers, and today we're looking at section 6.1 from the ZIL Intro to Differential Equations text, and it covers a review of power series. We're going to review some of the power series basics. You may need to go and crack open your Calculus 2 notes to review more, but this gives you some of the basics. And then at the very end, we solve a first order differential equation using a power series. So most linear higher order differential equations with variable coefficients can't be solved in terms of elementary functions. In other words, things that we can integrate even with tricks. So fortunately, we can use power series and a technique similar to the method of undetermined coefficients, which we covered in the section 4.4 of this text. So, power series. A power series in x minus a is an infinite series in the form summation from n is 0 to infinity of c sub n, so some sequence inside this series, times x minus a raised to the n, which if you expand it out, c0 x minus a to the 0 is just 1, so then plus c1 times x minus a to the 1 power plus c2 times x minus a squared plus ... and it keeps going in that fashion. Now, the index of the summation doesn't need to start at 0 or 1, right? We're looking at the infinite behavior of it unless you're trying to find an actual exact sum. So, the series above is a power series centered at x minus a. At this point in our math life, we'll be mostly working with power series in x centered at 0. All right, so something that would be centered at, I don't know, let's just say we had the series from n is 0 to infinity, and let's say it was x plus 7 to the n, right? So here, this series is centered at -7 because, remember, it's in the form x minus a. So in this case, to get that minus there, you'd have to break it up into x minus, -7. And that's why it's centered at -7. Cool. So what does that mean? That means it's going to, if you had a power series that, approximated a function, it would be approximated that function near values of -7. So if it's centered at 0, it approximates function values at x equals 0. Here are some important facts about power series. And in this form here, summation goes from 0 to infinity of c sub n times x minus a raised to the n. Convergence. A power series is convergent at a specified value of x if its sequence of partial sums, and the way we denote that is this set, it's the sequence of partial sums, and then that's in terms of x, if that converges. So what does this look like? The limit as capital N approaches infinity of the set of partial sums in terms of x. or the nth partial sum in terms of x, which would be the limit as capital N approaches infinity of the summation as small n goes from 0 to capital N of C sub n times x minus a, this quantity to the n exists. Cool, cool? If the limit does not exist at x, then the series is considered divergent. All right. Next up, interval of convergence. So every power series has an interval of convergence. The interval of convergence is the set of all real numbers x for which the series converges. The center of the interval of convergence is the center A of the series. Radius of convergence. The radius r of the interval of convergence of a power series is called its radius of convergence. If r is greater than 0, so it's positive, then a power series converges for absolute x minus a less than r, and diverges for absolute x minus a greater than r. If the series converges only at its center A, then r equals 0. If the series converges for all x, then we write r equals infinity, even though that's kind of a mathematical faux pas. A power series may or may not converge at its endpoints. So even when you run tests to find out if it converges on some interval, you still have to test the endpoints. Absolute convergence. In the interior of its interval of convergence, a power series converges absolutely. If x is in the interval of convergence and is not an endpoint of the interval, then the series of absolute values converges. So the series of absolute values is going to look something like this. You've got the sum from n, as n goes from 0 to infinity of absolute c sub n times x minus a to the n. Cool, cool? All right, so now let's just take a look at this interval of convergence business. So if you've got some line about x, all right, at the center, you're going to have some a, all right? So let's call this the center, and the center is a. Now, if this length here between a and this tick mark is r, then this value here would be a plus r. And then here, this would be a minus r. So what we have going on is you've got absolute convergence right here within the interval. Now, at the endpoints, it might or might not converge. We don't know. We got to test them. Outside of, so this here is absolute x minus a is less than r, okay? Now, out here, this is going to be divergent. And that's where you're outside of the interval from a minus r to a plus r non-inclusive. So these here represent where it diverges, all right? So divergence. And as far as the endpoints go, we don't know, right? You'll have to run a test on them. Okay, so speaking of tests, the ratio test. This is a great test, but it doesn't always work, but it is great. Convergence of power series can often be determined by the ratio test. So if we suppose that C sub n, that sequence that's a coefficient to the x minus a to the n term, is not equal to 0 for all n in the summation as n goes from 0 to infinity of c sub n times x minus a to the n, and that the limit as n approaches infinity of the absolute value of the ratio of the n plus first term to the nth term. So you have c sub n plus 1 times x minus a to the n plus 1 over c sub n times x minus a to the n in absolute value, which is equal to x minus a are not part of n, the n that's going to infinity, so they can be brought out in absolute value, times the limit as n approaches infinity of the n plus first term of that coefficient sequence to the nth term, that ratio. And if that is equal to some L, if L is less than 1, this series converges absolutely. If L is greater than 1, the series diverges. And if L equals 1, the test is inconclusive. That's when it's a big bummer. The ratio test is always inconclusive at an endpoint, which occurs at a plus or minus r. Cool, cool? All right, so now let's look at an example here. Find the interval and radius of convergence of the power series. So with this one, looks like a great candidate for the ratio test whenever I see a factorial, something to an nth power, especially when I see a factorial, I think ratio test. So let's check it out. In this case, just to identify what's what, notice that x is just alone, x to the n. So that must mean that a is 0, so it's centered about 0, this power series. And the c sub n is equal to 5 to the n over n factorial. Cool, cool? So what we need to do is evaluate the limit as n approaches infinity of the n plus first term divided by the nth term. So the n plus first term would be 5 to the n plus 1 times x to the n plus 1 over n factorial. Plus 1 factorial. This will be divided by 5 raised to the n times x to the n over n factorial. Now we can multiply by the reciprocal of that, so we'll get the limit as n approaches infinity of 5 to the n plus 1 times x to the n plus 1 over n plus 1 factorial times n factorial over 5 to the n times x to the n. Cool so far? Now, n plus 1 factorial is 5 to the n plus 1 divided by 5 to the n is going to just be 5, right? So we'll have 5, because n plus 1 minus n is 5 to the 1. And then same with the x, we'll have 5 times x times n factorial, making it one happy fraction, over n plus 1 times n factorial. Cool, cool? All right, and so the n factorials divide out to be 1, and the limit is not affected by the x, so as n goes to infinity, this limit goes to 0. 0 is less than 1, and so we have that it converges absolutely for all x. Okay, so that means that the radius of convergence is r equals infinity, and the interval of convergence I'll write it first as minus infinity less than x less than infinity, but normally you'll see it just as minus infinity to infinity. I wanted to just remind you that it's about x is what those parentheses are, you know, that interval has x in it. Okay? All right, so now let's look at this one, number 2, right? This one, the ratio test would probably work just fine, but just for the heck of it, let's go ahead and run. This is a geometric series because you could rewrite it as the summation as k goes from 1 to infinity. It's okay that it's not starting at 0. And notice that you have a 3 to the negative k. So you could put that 3 to the k in the denominator. And so really what you would have is you would have this whole thing, 4x minus 5 over 3 raised to the n. Now we know that things that are geometric in form are going to converge when the absolute value of what's being raised to the n is less than 1. Good so far? So to take that absolute value off, we would have negative 1 less than 4x minus 5 over 3 less than 1. And then what will we have? Beautiful. Negative 3 less than 4x minus 5 less than 3. So do you see that the radius of convergence, if you put this back into absolute value, you'd have absolute 4x minus 5 is less than 3. So our radius of convergence is r equals 3. Groovy? Now continuing to isolate the x, if I add 5 to each part of the inequality, I'll have 2 is less than 4x is less than 8. And then isolating the x, we'll have 1/2 is less than x is less than 2. And then when we go to check the endpoints, all right, so we're going to check x equal to 1/2 first. So when x is equal to 1/2, the summation turns into 4 times 1/2 minus 5 over 3. All of that is raised to the n. That's going to be equal to the summation as n goes from 1 to infinity of negative 3 to the n, negative 3 over 3, all to the n, which of course will just be the summation as n goes from 1 to infinity of negative 1 to the n. Good so far? All right. So by the alternating series test, right, this will be a series that alternates, you separate out the negative portion, and all that's left here would just be a positive 1, right? And so I know that that's going to diverge by the nth term test, because the limit as n approaches infinity of the non-negative portion of our alternating series, which is 1, is going to equal to 1, which is not equal to 0. So this diverges by the nth term test. And now, if we check the other endpoint, x equal to 2, we'll have the summation as n goes from 1 to infinity of 4 times 2 minus 5 over 3, all of that raised to the n. That's going to be the summation as n goes from 1 to infinity of 3 over 3 to the n, which is 1 to the n, which is just 1. And this, of course, diverges by the nth term test, because the limit as n approaches infinity of 1 equals 1, which is not 0. So it diverges by the nth term test. Now, it turns out that if you have a geometric series, it's always going to diverge at the endpoints. So we were able to write this whole thing as a geometric series. So I didn't really have to do this, but I thought it would be good review. So, final analysis here is that we found our radius of convergence is r equals 3, and our interval of convergence is what we found over here. And so 1/2 to 2, non-inclusive. Cool, cool? All right, perfect. Now moving on to the next bit of loveliness. A power series defines a function. So a power series defines a function whose domain is the interval of convergence of the series. if the radius of convergence is r greater than 0 or r equals infinity, then f is continuous, differentiable, and integrable on the intervals a minus r to a plus r or minus infinity to infinity respectively. Now, f prime of x, sorry, there's supposed to be a period there, and the integral of f at x with respect to x can be found term by term, term by term differentiation and integration. If y equals the summation from n equals 0 to infinity of c sub n times x to the n, that would be c0 times x to the 0, which is 1, plus c1 times x to the 1 plus c2 times x squared plus c3 times x cubed plus ... This is a power series in x, all right? Or if this is a power series in x, then the first two derivatives, right, are going to be y prime is equal to the summation from n equals 0 to infinity of n times c sub n times x to the n minus 1. And y double prime is going to be the summation as n goes from 0 to infinity of n times n minus 1 times c sub n times x to the n minus 2. Notice that the first term in y prime and the first two terms in y double prime, if we plugged in n is 0, each of them would zero out. And if we plug in n is 1, the second derivative would zero out. So they are 0. So we omit the 0 terms, and you end up with y prime is equal to the summation as n goes from 1 to infinity of c sub n, I'll put the constant first, times n x to the n minus 1, which is equal to c1 times 1 times x to the 0, which is just going to be c1. And then if I plug in n equals 2, I'm going to have c sub 2. I'll have a 2 for n, so 2 times c sub 2. And then x to the 2 minus 1 is x to the 1. Cool? And then I will have 3 c sub 3 x squared plus 4 c sub 4 x cubed plus ... And y double prime is going to be the summation as n goes from 2 to infinity of c sub n times n minus 1 times x to the n minus 2, which will be, and then when n is 3, we'll have c3, n would be 3, and then n minus 1 would be 2. So we would have 6x to the 1. And then I forgot my c2, my bad. So this would be c3. And then x to the 1. Cool. And then when n is 4, we would have c4 n is 4, so we'd have 4 times 3 is 12. So 12c4x squared. And it would continue in that manner. Groovy? Identity property. If the summation as n goes from 0 to infinity of our, sorry, it's all scrunchy. Write this better. The summation as n goes from 0 to infinity of c sub n times x minus a to the n is equal to 0. Okay, if the whole summation is equal to 0 and r is greater than 0, for all numbers x in some open interval, then it turns out that c sub n is equal to 0 for all n. Cool, cool? So that'll be important. We will use that fact, okay? Now, again, another fact we'll use. Analytic at a point. A function f is said to be analytic at a point A if it can be represented by a power series in x minus a with either a positive or infinite radius of convergence. Infinitely differentiable functions can be represented by Taylor series. And so with Taylor series, you have the summation as n goes from 0 to infinity of the nth derivative of f at a over n factorial. So that is your c sub n. I know it's complicated. And then that's times x minus a to the n, which is equal to f at a plus f prime at a times x minus a over 2 factorial. This one would, or 1 factorial, my bad. First derivative, 1 factorial, which is 1. This would be 0 factorial, which is also 1. And then x minus a is to the 1 power. And then we'd have plus f double prime at a times x minus a squared over 2 factorial plus dot, dot, dot. It would keep going on in that way. Now, a Maclaurin series is always centered at 0, which is nice. So that would be the summation as from 0 to infinity of the nth derivative evaluated at a over n factorial of x to the n. And then, or times x to the n. And then that would simplify to f at a over 0 factorial plus f prime at a over 1 factorial times x. And then f double prime at a over 2 factorial times x squared plus dot, dot, dot. Cool, cool? Beautiful. All right, so here are some series of interest to us. All right, so we've talked about e to the x before when we were deriving some of our solutions. So e to the x is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 and that will equal to the summation as n goes from 0 to infinity of 1 over n factorial times x to the n. The interval of convergence happens to go from minus infinity to infinity. And then cosine at x. We've also played with that a little bit in looking at Euler's formula. And this ends up being 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus minus dot dot dot, and then that would equal to the summation as n goes from 0 to infinity of, it alternates, so it'll be -1 to the n over, all those factorials are even, so we'll have 2n, that quantity factorial, and x is raised to the 2n. And the interval of convergence is minus infinity to infinity. Cool, cool? Then sine at x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus minus dot dot dot, and that's going to equal to, the summation as n goes from 0 to infinity, -1 to the n, and then that's going to be over, it's got odd factorials, so 2n plus 1 factorial, and then x is also all odd powers, that's going to be x raised to the 2n plus 1. The interval of convergence is minus infinity to infinity. Good so far? All right, so arctangent at x, inverse tangent at x is equal to. So this one is real similar to the sine at x power series, except it doesn't have factorials, but it has all the same powers, so that's kind of nice. So we'll have x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus minus dot dot dot, which is equal to the summation as n goes from 0 to infinity of -1 to the n over 2n plus 1 times x raised to the 2n plus 1, and I actually don't need parentheses around that 2n plus 1 because it's not a factorial. And this one has a radius of convergence from -1 to 1 inclusive. And here's a couple you might not have used before, but might be useful for purposes of this class. So I'm just going to give you the formulas. This is the hyperbolic cosine and the hyperbolic sine. So hyperbolic cosine at x is going to be really similar to the cosine at x, but it's all positive. So we're going to have 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus dot dot dot. That's going to equal to the summation as n goes from 0 to infinity of x, or 1 over 2n factorial times x to the raised to the 2n. Cool, cool? And that's good on the interval from minus infinity to infinity. The hyperbolic sine function, sinh x, is equal to, so it's going to be just like that sine at x power series, but no negative symbols. So we'll have x plus x cubed over 3 plus x to the 5th over 5 plus dot dot dot, which is equal to the summation as n goes from 0 to infinity of 1 over quantity 2n plus 1 factorial times x raised to the 2n plus 1, and that's good on minus infinity to infinity. And then just a couple more. I know I'm going fast on these. We're mostly going to just be utilizing them to find other stuff, all right? So natural log at quantity 1 plus x is equal to x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus minus dot dot dot. And so we'll have the summation as n goes from 1 to infinity of negative 1 to the n plus 1 over n times x to the n. This one goes from negative 1 non-inclusive to 1 inclusive. And then we'll take a look also at the Maclaurin series for 1 over 1 minus x. That is equal to 1 plus x plus x squared plus x cubed plus dot dot dot, which is equal to the summation as n goes from 0 to infinity of x to the n. And then that one is going to be, all right, so now it says I picked an example that says use an appropriate series from the table above to find the Maclaurin series of the given function. Write your answer in summation notation. All right, so a lot of times it's really easy to make this difficult. So basically, here is what we do. We have an e to the x series, right? We can always multiply an xn at the end. X e to the 3x is going to equal to x times the summation as n goes from 0 to infinity of e to the 3x. So that in turn will be x times, let's take a look. Everywhere we see an x in this one here, e to the x, we're going to go ahead and replace it with 3x. So we're going to get 1 plus 3x over 1 factorial plus 3x the quantity squared over 2 factorial plus 3x the quantity cubed over 3 factorial plus dot dot dot. Cool so far? All right, awesome. Now, let's take a look at what this is going to shake out to be. So, this one will be equal to, the trick with summations often is to keep them in terms of their powers. So this is 3 to the 1 times x to the 1 over 1 factorial plus 3 squared times x squared over 2 factorial. See the trend? Plus 3 cubed times x cubed over 3 factorial plus dot dot dot. Now I can go ahead and multiply in the x. So this is now going to be x plus 3 to the 1 x to the square over 1 factorial plus 3 to the square x to the cube over 2 factorial plus 3 cubed x to the 4th over 3 factorial plus dot dot dot. So the power on x is 1 more than the power on 3, and it's 1 more than what's in the factorial. So we can say that this is the summation as n goes from 0 to infinity of 3 to the n, x to the n plus 1 over n factorial. And remember that 0 factorial is 1. Cool, cool? All right. There we go. Beautiful. Now, next up, x over 1 plus x squared. So this one is going to be a little bit tricky, right? So remember that we could rewrite this guy as x times 1 over 1 minus negative x squared. So the negative part isn't being squared, just the x is. And do you see that's equivalent to 1 plus x squared? So this will be equal to x times the summation as n goes from 0 to infinity. We did this 1 over 1 minus x one here. Remember, it was 1 plus x squared. So everywhere we see an x, we'll put in an x squared. So now we're looking at this one. So this will be, I'll write this in the summation, 1 over 1 minus negative x squared. It's now in our summation form, which will be x times, well, we had 1 plus negative x squared, and the first x was to the 1 power, and then plus negative x squared, that quantity will now be squared, plus negative x squared cubed, plus negative x squared to the 4th, plus dot, dot, dot. Good so far? So that negative is going to make it alternate, right? So this will be x times 1 minus x squared plus x squared squared. So this is like x squared to the 1. And then we're going to have minus x squared cubed. Cool so far? And then we'll have a plus x squared to the 4th. And then minus plus dot, dot, dot. All right, so now we'll have x times 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th, and then minus plus dot, dot, dot. When I bring that x in, I will then have x minus x cubed plus x to the 5th minus x to the 7th plus x to the 9th minus plus dot, dot, dot. And that is going to give me the summation as n goes from 0 to infinity of negative 1. Let's see, the first term is positive, right? So negative 1 would have to be to the n plus 1 if we start at 0 for the index of the summation. And then x has to be odd. So x will be to the 2n plus 1. Groovy? All right. So there's our result. And then now, arithmetic of power series. Power series can be combined through the operations of addition, multiplication, and division, and we add, I actually forgot a little something here, so we add coefficients of like powers of x. We use the distributive law. And then we combine or collect like terms and perform long division. So here is an expression that we want to rewrite using a single power series whose general term involves x to the k. So here's what I'm looking at. I want the summations to start when x is raised to the same power, right? So the second summation, 3 times summation n goes from 0 to infinity of c sub n x to the n plus 2. When I plug in n equals 0, I have an x squared, right? The first summation, I plug in that lower limit of the summation n equals 1, I get x to the 0. So it would take a couple of terms, right, to get to x squared. So let's find the first couple terms. So here we go. We would have this summation here going from n is 1 to infinity of n times c sub n times x to the n minus 1 would equal to, the very first term would be n equals 1. So we'd have 1 times c sub 1 times x to the 0, which is c1. And then the next term, when I plug n equals 2n, I would have 2c2 times x to the 1. And then my next term would be x squared, which is what I want. So now I'm going to write it as the summation, but now that summation is starting from 3 going on to infinity. Cool so far? And then it's the same thing, n times c sub n times x to the n minus 1. Now, I don't need to worry about that second one changing anything except for using a dummy variable to change the limits of integration so that they're both starting at the same thing. So this is where we're going to try out. So for this one, the trick is when you think you're there, look at the power on x and then let k equal to that power on x. So see that the power on x is n minus 1. So for this series, we're going to let k equal to n minus 1. Now, if k is equal to n minus 1, n would in turn equal to k plus 1, correct? And the lower limit of integration is now n equals 3, right? So where would k start? When n is 3, k would start at 2. Cool so far? All right. Now, let's take a look at this other summation. We have 3 times the summation, n is 0 to infinity, times c sub n times x to the n plus 2. I already have the x squared where it starts. So what I'm going to do is I'm going to let k, yes, k, equal to n plus 2. And so that means that n would equal to k minus 2. Good so far? Now the limit of that summation starts when n is 0. So k equal to 0 plus 2 equal to 2. Bingo! Both of the k's start at 2. So I can combine them. So this is going to give me the first couple terms, which were c1 plus 2c2. I'm looking at this first one. And then plus the summation from k equals 2, right? And then to infinity. N, remember, for this one is k plus 1. So c sub n would be c sub k plus 1. And then x would be raised to the k. And now the second summation. I'm going to bring the 3 inside. K starts at 2, goes to infinity. We have 3 times n, which is, in the second one, k minus 2. So we're going to have, and this is not n, it's c sub n. So we would have c sub k minus 2, and then x is raised to the k. Cool so far? So now they both have the same starting point on the summation and the same power of x. So we're in business. So that's going to equal to C1 plus 2C2. Plus, we'll do one happy summation as k goes from 2 to infinity. We've got k plus 1 times c sub k plus 1 plus 3 times c sub k minus 2. All of that is times x to the k. So we made one happy summation. And guess what? That's all we were asked to do. So we are all done with that problem. Okay, so now example 4. Find a power series solution, y equals summation, n goes from 0 to infinity of c sub n times x to the n of the given linear first order differential equation. So we have 4y prime plus y is equal to 0. So we need to figure out what is y and what is y prime, all right? So do a little side work. Y, remember, is equal to the summation as n goes from 0 to infinity of c sub n times x to the n. Good so far? Now, y prime is going to equal to the summation. Remember, it's going to start at 1 because the first term will zero out as n goes from 1 to infinity of c sub n times x to the n minus 1. Cool so far? So, remember, we want to combine these summations, so why don't we get the work done here so that they both have the same starting point and they have the same power on x. Cool so far? So let's take a look at when I plug in 0 into y, I get c sub 0 times x to the 0. When I plug in n equals 1 for y prime, I get c1 times 1 times x to the 0. So for the first one, we're just going to let k equal to n. Cool so far? And so, of course, n will equal to k, and the summation will start at 0. Groovy? The second one, we're going to let k equal to n minus 1. So that means that n would equal to, good, k plus 1. Well, n starts at 1, and so going up here, k would be 1 minus 1, which is 0. Groovy, they both start at 0. All right? So y prime is now going to be the summation as k goes from 0 to infinity of c sub n. Well, we have to write it in terms of k, so that's going to be k plus 1. And then times n, which is k plus 1, times x to the k. And then that other one, y, we're just switching out the n's for k's. So we'll have the summation as k goes from 0 to infinity, c sub k, and x to the k. Groovy? All right. So now what we do is we want to substitute these summations in to our given equation. So we have 4 times y prime. Well, y prime was the summation as k goes from 0 to infinity of c sub k plus 1 times k plus 1 times x to the k. And then plus y. Well, what was y? Y was the summation from k, as k goes from 0 to infinity, of c sub k times x to the k. Groovy? And then all of that has to equal to 0. All right, so now let's combine those summations, right? We already did the work ahead of time. And so here we go. I'm going to have the summation as k goes from 0 to infinity. I'm bringing the 4 inside. So we're going to have 4 times c sub k plus 1 times k plus 1. We're going to factor out the x to the k to the right. So from the second summation, I'm going to have plus c sub k. And then all of that would be times x to the k, and it's all going to equal to 0. Groovy? Now, that's an identity. Remember back here? Where was that? Arithmetic, identity. Here it is, this one here. So if you've got a summation and it's equal to 0, your radius of convergence is greater than 0 for all numbers x on an open interval, then c sub n is 0 for all n. So what does that mean? We will go ahead and we're going to equate the coefficient to the x to the k term equal to 0. So we're going to have 4, I'll write it as k plus 1 first, times c sub k plus 1 plus c sub k equal to 0. Well, that means if I isolate c sub k plus 1, I will have negative 1 over 4 times k plus 1, and then times c sub k. So it's recursive, right? Now what we do is we start finding some terms, because remember k started at 0. 1, 2, dot, 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 right? So let's plug in some numbers and let's figure out what's going on. So here we go. If k is equal to 0, right, then c sub 0 plus 1 would be c1. Everywhere I see a k, it'll be a 0. So I'm going to have negative 1/4 c0, because k is 0. Groovy? That one wasn't bad, right? All right. Now, if k is 1, we'll have c sub 1 plus 1. So we'll have c2 is equal to negative, I'm working on the original, 1 over 4 times 1 plus 1 is 2. Good so far? Times c sub 1. But what is c sub 1? Well, that'll be negative 1 over 4 times 2. c1 is negative 1/4 times c0. So that in turn will be positive 1 over 4 squared times, let's write it as 1 times 2 just for fun. I'm thinking that might end up being a factorial. And then we'll have times c sub 0. c3 similarly will be negative 1 over 4 times, k is now 2. So 4 times 2 plus 1, that would be 3. And then times c2. Well, that would now be 1 over 4 times 3 times 1 over 4 squared times 1 times 2 times c0. But what is that? That's going to be 1 over 4 cubed times, look at that, 1 times 2 times 3. You see the trend here? And then we have times C0. Everything's in terms of C0. So that would just keep going on and on and on as such. So let's see if we can write this up as a nice trend here. So y equals to C0, whatever C0 is. And then minus, I'm going to write it as 1 over 4 times 1, C0 for my C1. And that has to be paired with x to the 1. And then, what are we going to have next? We're going to have a positive, right? So this is going to be plus 1 over 4 squared times 1 times 2, C0 times x squared. And then minus 1 over 4 cubed times 1 times 2 times 3, C0 times x cubed, plus minus dot dot dot. So y is equal to C0, right, minus 1 over 4 to the 1 times 1 times C0 times x, plus, couldn't we write the 1 as 1 factorial? Couldn't we write over 0 factorial here and 4 to the 0, right? And continuing, we would have 1 over 4 squared times 2 factorial, c sub 0 x squared, minus 1 over 4 cubed times 3 factorial, c sub 0 x cubed, plus minus dot dot dot. Now let's go for our summation. So y will equal to the summation. We can factor out a C0, right? It's in all the terms. Move that over. And then this is about k, and it's going from 0 to infinity. Now we're going to have to figure out, it's alternating, so -1, if I put that to the k, and I start at k as 0, I think that's going to work just fine. It's going to be over 4 to the k, right? And then times k factorial, and then times x to the k. Now, playing around, this is the hard part, right? We'll have c sub 0. The summation, k goes from 0 to infinity. We have x is raised to the k, 4 is raised to the k. So we will have -1 to the k over k factorial, and then times x over 4 to the k. Now, does that remind us of anything? Well, if you look back at the list, right, wouldn't e to the x alternate if it was e to the negative x, right? See how it has a 1 over n factorial x to the n? It's real similar. And so ours alternates, but it has that n factorial. And so if we plugged in -x over 4 into that whole system, and this is C0, sorry, then that's our answer. You'll see that it is equivalent. Cool, cool? All right, so anyway, this is just kind of a really fast series review. My website is mathchick.net. And if you click on my Math 155 class, you can access my annotated notes for Calculus 2. They're not the neatest ever, but they'll give you the information you need if you need to review some series. So anyway, I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, hit that like button and please subscribe. Bye.